Welcome back, Contemporary Math. We are in chapter 3B, putting numbers in perspective. So we are going to do a few things to compare numbers. So we're going to start off talking about scientific notation and talk about how to calculate things with scientific notation real quick. They do perspective through estimation, perspective through comparisons, and the last thing that they do is, perspective through scaling, I believe, is the three things that we're going to go through after we do a little bit of work with scientific notation. So when we write numbers in large scale or small scale, and we've already done a little bit of work with metric, there's this thing called scientific notation where we write things in powers of 10 or multiplied by powers of 10. So I don't really care for the definition, to be honest. So they put scientific notation as a format in which a number is expressed between 1 and 10. I would say like expressed as 0. And I don't like the fact that they put 10 in there, to be honest, because we're going to do 4, 5, 6, 8, 9 is what I would think. There is some numeral in front of the decimal place. So there is a single numeral in front of the decimal place, and then there will be some decimals, and it is not 0. So if it's 0, we still have to move the decimal over. So I think the best way, most of you probably have some sort of experience with this, but the best way is to sort of jump into this and get to the example. So if we look here, I want my decimal. Yeah, let's go with the red for the desired. So that's the start. The end goal is to put it. 9 is right in front of the decimal. I have one numeral in front of the decimal. The part should look like 9.8. Everything else is zeros. I don't have to worry about them. Going time. I'm asking myself, what power of 10 do I have to multiply 9.85 by? There are 3, 6, 9, 12, 15 spots I went through. So I'm counting the number of spots I moved the decimal over. So this one got larger. So we were multiplying by powers of 10. This one is smaller. So we will start decimal starting there. I want to end there so that my number looks like 4.67. Multiply this by 10 to a power. So if I move the decimal left, it's positive, but if I'm moving the decimal right, 7 spots that I moved it. It has to be -7. And so this is sort of like you're dividing by 10 to the 7th is another way to think about that. We talked about negative exponents. -7 would be 1 over to the 7th. So we're starting out here in standard notation, and they want us to write it in scientific notation. Now we're going to go the other way around. We're going to start in scientific notation and rewrite this in standard notation. 6.7. And this is times 10 to the 5th. This is a positive 5. So if it's positive, this number should be getting larger. It should be a large number. So 1, 2, 4, 5. I have to move it 5 spots to the right to get this, make it larger. And I have to rewrite this. My comma in there. 670,000. All right. And if we look at this, hopefully the first thing you notice is this is now a negative exponent. So instead of moving to the right, this one, spots. This is my and please like give me like this thing over here, right? Don't give me like something you did some work on. That's not your final solution. I don't know where your decimal went or where it is. This is not easy to read or grade, right? Don't give me your work. Or give me your work. Sorry, that's probably the wrong thing to say, huh? Give me your work, but also show the solution, right? Get to the end. I don't know what to say. That's what I should say. Get to the end. Definitely show your work. There are 1.49 million residents in San Antonio who each produce approximately 1.8 pounds or 0.009 tons of garbage each day. Your friend calculates the total garbage produced by San Antonio residents and reports their answer is 134 tons. Does that seem accurate? So this would sort of like estimating just the powers of 10. So if we look at this, we look at 1.4 people producing that many tons of garbage each day. So if we want to get to how much garbage total, we're going to multiply the number of people by the number of tons. If we're in the millions, this is something that is going to be times 10 to the 6. All right, that would be millions. The other number, 0.0009. I'm going to round this up. So it's like because that 9 is closer to the next one. I'm going to round it up a little bit. If you have to do it, you can round it. The correct spot. It should be 3 spots. This is a 10 to the minus place that this thing is going in. And I think I mentioned it before, but if I have 10 to the 6, the rule here is that we can add these exponents. So minus 10 to the 3rd. And so his answer should be in 10 to the 3rd, or it should be in thousands, and he's getting something that is in the hundreds. And so does this number seem accurate? No, it does not seem accurate. He should be getting something in the thousands. Is that what we're... well, that's coming up. Okay, never mind. I was thinking of that thing. So if you want to add and subtract in standard notation, or in scientific notation, there's not really an easy sort of way or shortcut to do that. So you just have to convert back to the standard notation and compute it. But if we are multiplying and dividing in scientific notation, there are some shortcuts we can take to keep it in scientific notation. And so this has to do with, there are 2 sort of rules that happen in math when we multiply. So one of them sort of says, it doesn't matter how I group things. If I multiply these 2 things together and then a third. So you can throw in numbers if you want. 2 times 3 times 5, right? If we do that first. Or if we do 3 times 5. Either way, we should be getting 30 on either side. So these are sort of rules that we have. We can drop parentheses. We can rearrange things, right? A times B is B times A. 3 times 4 is the same thing as 4 times 3. So there's these sort of rules that we use when we multiply. I don't know if we'd like really think about using them, but we sort of do. And we can sort of apply them here it doesn't matter what these parentheses are in. Everything here is being multiplied. There's like this thing, this thing, this thing, and this thing. There's 4 things getting multiplied here. And so it really doesn't matter what order we write them in. We get 4.56 as being multiplied by the 2.7. Like the 10 to the 6 and the 10 to the 7 sorted together. And this, you will probably have to grab a calculator and figure out what 4.56 is. Times 2. Let me make sure I read that. 73. I get something like 12.4488. So I'm going to round that to 12.45. The thing I was talking about earlier. If I have 10 to the 6th and 10 to the 7th, I can think of this as 10 to the 6 plus 7 is going to give me 13. So now I have this thing. It looks like it's in scientific notation, almost in scientific notation. Look at this. This is 12.45. And this side 13. This is not in the right spot. So we have to convert this to scientific notation. We have to put that decimal right in front of that one. Okay. And so this is something that is a bit difficult, but this is the sort of way that I think about it. If we go from the number like 12 to 1, and it's going down like one decimal place. So if that's going down 1 decimal place, you have to go up. So instead of that 13, I'm going to write 14. Okay. So if this thing decreases, this thing has to increase. And the next thing is division. So I'm looking at this thing, and I have sort of 2 sort of notations on here. So if you're using a calculator, it's probably not going to have this notation. It might have this notation. So some calculators do have that notation, but most of them, I think, have this notation. And this little e takes place of the times 10 to the, and the next thing is your exponent. And so I think the button on the calculator is, so it's this blue one, if you're using the TI 80s models. It is not a lowercase e, so it is like a case sensitive sort of thing. This is the natural log, the natural exponential. This is the scientific notation. So you do have to be careful with the case. It's got to be uppercase. So we're starting this thing. And this is sort of like I was talking on the previous thing. We have a lot of rules we can kind of use to our advantage. So when we multiply fractions, we multiply straight through top and we multiply straight through bottom. So we can kind of think about this as like separating the fractions. And we can kind of think about these things separately then. And that might be kind of advantageous because we have 4.43. 4.43. And we're going to divide that by 5.78. And this is giving me something like, I'm going to go, I guess, to 4 decimals. This thing over here is. This thing over here, I kind of previously, this is 11 minus 7. So if we're dividing something with the same base, these are both base 10, we can subtract the exponents is the sort of rule that we have for exponents. Okay, so we're fixing this thing up. 0.7664. 11 minus 7 is going to give me 4. So this is an almost scientific notation. So there's still one sort of little thing we want to do. We want to move this thing. Instead of 0.7, now this thing is 7.64 times 10. And this is the thing that we have to think about. We're converting this larger. Smaller. If this is getting smaller, we're going from 4 to 3. A little bit, I want to go a little bit maybe over like why these are things, right? And if you want to demonstrate it to yourself, good way to do it. 2 to the third times 2 to the fourth. If we have a like base, 2 times 2 times 2, and this is times 2 times 2. So I have 2 multiplied 3 times, I have 2 multiplied 4 times, I have 2 multiplied a total of 7 times. So if we have a like base, we are going to add those exponents. 3 plus 4 will give me the 7. Same thing with 3 squared. If I write 3 to 1, and then I write 3 twice. There's this thing I really like to do called simplifying. And you might notice what we're doing is we're essentially doing 3, 7 minus 2. So we're going to have 3 to the 5th on top. And so those are where those sort of exponent rules are those rules are coming from. And I know I went through that real quick. But that's sort of where that principle is coming from. You don't have to take my word for it, right? You can demonstrate these things to yourself. Okay, so now we're going to do, we did a little bit with scientific notation. Now we're going to do the 3 things with the perspective. So the first thing is perspective through estimation, giving meaning to numbers. So order of magnitude. So this is sort of like what we were doing with that first problem with the tons of garbage in San Antonio. These are broad ranges of values. These are like the powers of tens that we're talking about, like in the millions and the thousands and the hundreds. So we're talking about 10 to the 10 to the 18. We would say this is 5 orders of magnitude larger than 10 to the 18. Larger. Okay, example 4. Population in Texas is approximately 28 million. If we assume that everyone in Texas had about 2 servings of ice cream per week and each serving cost about $2, then find an order of magnitude estimate to predict how much money Texans spend on ice cream each year. Okay. So we know the population. we know they're spending what, $2 each week or $4 each week. So if they're spending $4 each week, we want to know their annual spending. So in order to get to the annual spending, we've done a few of these, but if this is per week and we want to get to per year, $4 each week, and you're spending this each week, you're going to spend this 52 times throughout the year. So 4 times 52 should be getting you, what, 4 times 52? Something that's 200, 208, right? So this is each person is spending that amount. And the population is approximately 28 million. So we're going to end up multiplying this number by 28 million. So if we think about 28 million, millions would be n times 10 to the 6. If we're adding another 10 spot to that, it should be times 10 to the 7. Oh, let's write it out. 1, 2, 4, 5, 6. So if you notice, this is going to be a times 10 to the 7th magnitude. This thing is going to be a, what, times 10 to the second magnitude. So my solution should be somewhere in, it's like times 10 to the 9th magnitude. So if we're talking about that, billions, right? Three is thousands, 6 is millions, 9 would be billions. Ooh, here's a unit analysis problem. So we have 1 billion seconds. So if you're just counting 1, 4, 5, 6. Well, count to 1 billion. Doing that. 3, 6, 9. There are 9 zeros. That is 1 billion seconds. Okay. Minutes. That's in 1 minute. So the first thing I'm doing is I'm taking 1 billion and I'm going to divide it by 60. That's going to give me 16666. And like 2.67, right? It's the 6 repeating. And this now is in minutes. So your 1 billion seconds is what, 16 million minutes. Now I'm going to go from minutes to hours. So I'm going to put my minutes on the bottom. I'm going to put my hours on top. There are 60 minutes in 1 hour. So now I'm taking this number, dividing it by 60 again. And I'm doing this on a calculator, so I'm not rounding anything. I'm just letting it crunch it. So this is 277,777 hours. So I'm doing this one at a time. I normally just did this like one sort of swoop is what I was doing previously. So now I'm breaking this apart a little bit, maybe more than I have previously. Ooh. Let's get the answer back. So that answer, now we're in hours. We want to go from hours to days. There are 24 hours in 1 day. The next thing we're dividing by is what, 24? 115. 11,574 and some change. Days. Okay, there are, I'm going to go with 365.25 days. I'm going to put that every 1 year. So how many years is this going to be? I'm getting 31.688. So this is, if you're counting, just 1, 2, right? 1 every second, and you don't ever sleep, don't ever eat. It's going to take you 31 years. So someone has $1 billion in a room in one, and they challenge you to take them out one by one. Don't fall for it. Okay. I need 1 billion seconds. Here is a chart that might come up in the future. Is there any way to focus this a little better? No. Okay. So we are going to start talking more about energy in these next problems. They have this table of selected energy comparisons here. So you might notice that there are these energies from like eating a candy bar to running an hour to burning oil. They have the U.S. and world energy consumption, annual energy consumption. They have the energy generated from the sun. So these are all sort of weird things to maybe compare, but we can all measure the energy in joules, so we can all compare them like sort of mathematically. And we can come up with some weird scenarios with machines that maybe don't exist that convert one to the other, but we can compare them. Okay, so the U.S. population is approximately 300 million, and this is back when I wrote this, so this is probably went up since then. So the U.S. population is approximately 300 million, and the U.S. annual energy consumption is 1.10 times 10 to the 20 joules. The world population is approximately 7 billion, and the annual energy consumption from the world is 5.3 times 10 to the 20 joules. Compare the U.S. population to the world population and the U.S. energy consumption to the world's energy consumption. So there's two things that they're asking for. They're giving us a bunch of information, but let's focus on, we're comparing U.S. population to world pop, and we're going to compare U.S. energy to world energy. So the first thing they say is compare the U.S. population to the world population. So what we're doing is we're creating this sort of thing, dividing one by the other, comparing the two. World population is 3 times 10 to the 8. It's coming from this, then, oh, yeah, I have it written there. There we go. 6 would be the million, and then these 2 zeros would give you 2 more, is what they're basically doing. And then the world population is, it's somewhere in there, 7 billion, 7 times 10 to the 9th. So this was the division of scientific notation that I was talking about previously. we have 3/7. So we have 3/7. And this is going to be 8 minus 9 would be 10 to the minus 1. So we're going to have to move it over a decimal place. So if we do 3/7, 3/7 is going 0.4285. We're still going to move it over a decimal place. So this would be 0.042. So what this is telling me is the U.S. population is about, if we convert this to a percentage now, would be about 4.28%. We should round that up, 4.29, sorry. Okay, now we're going to look at the energy consumption. So we want to compare U.S. energy to world energy. The U.S. annual energy consumption gives it right there 1.0 times 10 to the 20th joule. The world energy consumption is 5.3 times 10 to the 20th joules. So this, again, I can do the 1 over 5.3. I can do that separately from this times 10 to the 0. This sort of thing is just a really fancy way to write 1. So we really don't even need to worry about this. All we really need to worry about is the 1 over 5.3. So I'm getting like something like 0.1887 and 68. So if I want to convert this to a percentage, we are using about 18.87%. So again, I think our world population was where we account for about 4% of the population, but we're using around 18% of the energy that gets used. Okay, so now we're going to be inventors. We're going to invent a machine that can metabolize candy bars and convert them into electrical energy. How many candy bars are required to supply electricity for one house for 1 day? This is from the table. The energy released from metabolizing a candy bar is about 1 times 10 to the 6 joules, and the average electrical energy use. Oh, I got the, never mind. I don't know. I threw that table in there this time around, and I guess I threw in the mounts from the table and the problem. So I guess we don't need the table. But on a test, you might be expected to read a value off of a table. That's not a complicated table. It's got a word phrasing what it means, and then it's got the energy in joules, right? So we want to know how many candy bars would be required to supply a home. Okay. And so one house is what, 5 times 10 to the 7th joules. And one candy bar is 1 times 10 to the 7th joules. Yeah, I want to step back and I want to do this probably more like from a unit analysis sort of approach. If one candy bar to y joule, I can say something like 1 joules. So you can probably figure this out without doing unit analysis, and if you can, fair enough. But I know I want to end up with candy bars on top. And I want to know how many candy bars to supply one home. How many candy bars per house? And this is 5 times 7 joules. And what this should be telling us is that we're dividing these two things. So if you just jumped right to this, you said that it requires like 5 times 7 joules to supply a house. And one candy bar gives you 1 times 10 to the 6 joules. You might notice we have 5 over 1 here. We have times 10 to the 7 minus 6. We're going to have a 10 to the first power. Woo! So that's an Amber Alert. Oh, man. I miss the, when we had live classes, it used to be like, ding, ding, we could see whose service was the fastest. So 5 over 1 is just 5 times 10. 50 candy bars per house is what we're at here. So if you want to supply a house with power, it will take you about 50 candy bars per day. So that was daily consumption. Okay. There's one last sort of little thing we're going to go over. And so I believe that was perspective through comparison. Did I just jump over that without saying what it was? I might have. Yeah. Perspective through scaling is the last thing. Become a lizard. No, not those types of skills. Verbally. So there are three, I believe, 3 different sorts of ways. Yeah. Well, another Amber Alert. Okay, so there are 3 sorts of ways this book likes to sort of phrase things through a scale. Verbally, they will describe the scale in words like 1 centimeter equals 1 kilometer. Or they could give you the equation, right? This is the sort of equation we're talking about. Graphically, they'll give you a little mini ruler on a map. A little ruler on there, and they'll say like this is 1 kilometer. When you do like a little map, they'll give you a little scale. And so they would measure out, I could do a centimeter. I think I got centimeters on here. Do it more accurate, probably. And they would give that to you on your little map. The other thing is the ratio. There are 100,000 centimeters and 1 kilometer. So they could say something like 1 to 100,000. You might notice that the ratio, the scale ratio doesn't have any units. So it's just like 1 to something. 1 parts to something other parts. Kind of like when you're baking, they just give you like sort of ratios, things with certain recipes. Especially when you get into like, what's it, bread making and stuff. I know everyone started doing that suddenly. But you measure by weights and ratios is a lot of what it is, depending on how much you need. There's no set. What do I want to say? Units is what I'm trying to think. There's no set units on the ratio. Okay, so we're using a map. It says 3 inches represent 1 mile. What is the scale ratio of the map? Okay. So we're comparing. So the first thing we really want to do, if we want to know the ratio, there are 100,000. So let's review something like this. We're going to 100,000. And then when we talk about the ratio, same thing. What we want is for these things to be in the same units so that we can compare them. And so here we're going with inches and miles. We really want to convert the larger one to the smaller one. So we want to start with 1 mile. You probably have to pull up your table. I'm not expecting you to know conversions. 1 mile, the first thing in that conversion, we can go from mile. So 1 mile is going to give me 5280 feet. And so the next thing we're going from miles to feet, and then we can go from feet to inches. There are 12 inches in 1 foot. And so this should simplify out, just to double check. Simplify out those units, we should be left with something in inches. And so if we multiply 1 by 5280, so 5280 by 12, actually, probably gonna multiply there. 63,360. Okay. And so this map says 3 inches to 1 mile. And so we're going from 3 inches to 60 inches. So we don't want to write the inches anymore. 3 to 60. We drop the units to talk about the ratio. They are in the same units, we can drop them to talk about the ratio. And then now we want to talk about this ratio. These are both sort of divisible. If I gave them to you as like a fraction or something, we could reduce both of them. So instead of saying 3, we can divide 63,360 by 3. We divide this number by 3, we should get 21,120. Divide this by 3, we can get 1. So if you can reduce it, it's a good idea to sort of reduce it. And that is the final problem in this section. I will see you in class soon.